Hello, class. All right, so we're going to talk about something called data fitting, which is, we've got lab 2 on this topic. And what I'd like to do is go over just kind of 2 examples of, things that would be realistic labs. Actually, one of them is something we will actually do later, and the other is a lab that we could do, but we're not going to this semester. So these are realistic kind of problems. And I'm going to start out. Let's say we have a spring that is attached to like a rigid object. And say we place a mass on the spring. What's going to happen is it's going to lower, the spring's going to lower it a certain distance. We'll call the distance that the spring stretches, we'll call that x. And we'll talk more about springs later, but I'm just going to give you an equation that, here it goes. I'll just write it down first. So we'll cover this stuff later, but basically the structure of the spring is related to how much mass that we attach to it. And basically the rule is that these are proportional to each other. Like say we hang, say 50 grams, and the string stretches 1 centimeter, then if we hang 100 grams, it'll stretch 2 centimeters. Twice the mass, twice as much stretch in the spring. G is just that, acceleration due to gravity. We've talked about that before. And K is a property of the spring. It's called the force constant of the spring, or just, very often called just the spring constant. Okay. So let's say that we have an experiment where we have a spring and we want to know what the force constant of that spring is. And so one way we could do this, we just solve this equation for K. So K is mg over x. Okay. Now, we could attach a known mass to the spring and use like a ruler or something to measure how much it stretches, and then just plug those in. And that would give us how much stretch there is in the spring. And that is a way to measure the force constant of the spring. But it's not ideal because, all measurements have errors associated with it. And so if that's all we did, we'll get a result, but it might not be a very good one. There could be significant errors. And probably the biggest error would come from measuring x, the stretch of the spring. You could buy mass sets, like we have them in lab, where they come, like it's labeled, 50 grams or 5 grams or whatever. So we'd expect the errors in the mass to be very small. G is a known value, but x could be, the biggest source of error. And that's important because if you're measuring something with a ruler or a meter stick or something, when you make mistakes or errors in the measurement, which always exist, you might overestimate it with one measurement and then underestimate it the next. There's really no reason we'd overestimate things rather than underestimate them. And so a good way to do this experiment, if we want to know the force constant of the spring, would be to repeat it several times. And actually a lot of errors will kind of cancel out that way. Like if you have a list of measurements, it's like some of them are going to be too high, some are going to be too low. And if you take all the data into account, you can actually reduce the error, these measurement errors, to a surprising amount. What we'd want to do is take several measurements. So the experiment is going to look like this. The variables in the experiment are the mass and the stretch of the spring. And we control the mass. Let's say we have, 50 grams, then 100, 150, 200. We'll stop here. Say we'll do 5 measurements. So you just keep adding 50 grams every time. Watch the string, record how much it stretches, and then that would be our data that we have from the experiment. And the question is, how do we get K out of this data? So we want to use all our data and get a value for K. Now, one thing you could intuitively do is calculate K for each of these masses. Like plug in, we'll have mass and the stretch and the spring. So I plug those in, we can get a K for each of these measurements and then take the average. But there's a better way to do it, to kind of take all the data into account at once. And what we want to do is we want to first make a plot of this data. So I'm going to erase this one. This is our basic equation here. And so we should expect this plot. Here, I'm going to actually draw this. Now we're controlling the mass. This is the independent variable. And then the amount of stretch in the spring depends on how much mass we apply. So this would be mass, let's say in grams, and X, let's say in centimeters. We're definitely not going to have a spring where we attach a mass and it's going to, stretch a meter. So like realistically speaking, these would be the kind of units that we'd be using. We're not going to have kilograms either. So we'd want to plot it like this. And what we'd expect, if there is no mass, then, we don't have a data point here exactly, but we should expect that point to exist on the graph. If there's no mass, the stretch should be 0. But then here we have 50, 100, 150. So here are our masses. And when plotting them, I'm just putting the numbers because, the axis is labeled with the units. You never want to neglect units in a graph. And we'll see why. It's going to actually be very important here. And now, we'll have data points that might look like this. We should expect this graph to be basically linear. Because if you double the mass, you should get twice as much stretch. So here we doubled the mass, so the stretch should be about twice as much. It's not exactly, though, because there will be errors in the measurement. And then what we want to do is, we're going to do this on a computer. We have our data, and so we can, have this table and actually plot this data. And I think I will make a separate video, just like doing a screen record, using a spreadsheet to plot this data. And one thing that's nice about all these computer programs nowadays, you can even do this with a calculator, where you can find the best fit line. So you can tell the computer to plot the best fit line, where it's going to kind of pass through. It's kind of tricky to define what the best fit line even means here. Real briefly, let's look at this point. This is a little above the graph. And let's define the distance from, say we have the line. We have some line that is in the form of y equals, I'm actually going to call it ax plus b. I don't want to use m because that might be confused with mass, but it has a slope and an intercept. So let's just say we have this line, and if we plug in, we're plotting on the horizontal axis, we're plotting the mass. So x for this first data point would be 50, and if we have a line, once we plug in x, we can find the y value, which would be, I'm going to exaggerate this. Let's say the data point is here. So if we plug in 50, we'll get a point on the line right here. And let's call this D1, the distance between that point on the line and the actual data point. And then point 2 might be a little below the line, so we'll call that D2. So we'll define D in general, or say just DI. That would be, let's see. Well, we'll say like from the actual data point, I'm trying to just come up with a name for that. You know, let's just call that Y. I'll write it like this. Okay, so the distance, that distance D, would be the Y value for the data point minus the Y value for this line. Okay. And so the idea is, if our data falls perfectly on this line, all these D values are going to be 0, and the data is perfectly linear. But that's not going to happen in practice. And so intuitively, you might think we want to find, and again, if we pick a different line, like if we change the slope and intercept, all these D values will change. And intuitively, you might think our goal is to just make D as small as possible. But that actually does not work. Just a quick example of why not. Let's say this is your data point here. These are your data points. And I could draw a line like this, and if we add up all the D values, we could get something very close to 0, even though this line is a horrible fit for that data. And the reason why is if you look at this point, where we have like Y data minus Y line, this is a very large negative value for D, and this is a very large positive value, and so these two could cancel out. And so yeah, clearly this method of just trying to add up all these D values and minimize them, that does not work. So, and the reason is these D values can be positive and negative. But like having a really bad data point here doesn't cancel out another data point here just because they're, opposite sides. And so what we want to do is make all these D values positive. And so the procedure is you square all the D values. And then you can add them up and get some value. And what you want to do is adjust these parameters A and B to minimize that, let's call it sigma D squared. We want to minimize that. So this is a function of A and B. And so you want to play around with these values until you minimize this, this quantity here. And you might have heard this expression before. It's called the least squares regression line. And, this name is very suggestive. Like here, squaring all these things, and the least squares, we're trying to minimize this. Now, the good news is the computer does this for you. Just to be clear, though, I said you kind of want to play around with these numbers until you minimize this. That would be one way to do it, this kind of trial and error approach. But that's not, there's actually a formula that you can use. So you can just take your data points and actually plug these data points into this kind of complicated formula, and it'll give you the slope and the intercept directly. So it's actually just a known procedure. But anyways, that's the idea. So I want you to kind of have some understanding of what this best fit line is, or this least squares regression line. But you don't have to do any of that. It's the computer. I'll record a separate video where I do this on the computer and just have the screen record. So because this is something we will be doing fairly often in labs, which is why we're doing it now. Okay. So the computer, let's just say we know how to do that now. So we plot our data. I'm going to plot these data points showing some errors because they will exist. All right, so here's our data. The computer finds the best fit line, and it'll tell us what this best fit line is. The computer will say like y equals whatever number a is plus the intercept, whatever that is. And now the question is, how do we get our goal is to find k. So how does this best fit line help us? And I'm going to do it, let's look at, back to our equation here, showing how these variables are related. We can, in this case, we can solve for x. Because normally we're applying like y is a function of x. Well, in this case, we can think about like our vertical, this is our vertical scale, this is our horizontal scale. And so let's solve for the vertical scale, which is x. So I'm going to rewrite this equation in a particular way. So x equals m over k. Sorry. Let me see how I want to actually do this. Yeah, we're plotting m, or the data involves m and x. So I'm going to say x is equal to g over k times m. So again, that is the exact same equation, we just rewrote it algebraically. So we divide both sides by k to get x by itself. And this, this is a linear equation that has a slope of g over k, and we can write plus 0. That would be our intercept, should be 0. So when you do this, like if you were actually doing this lab, when you get your best fit line, b should be very close to 0. It will not be exactly 0, but should be reasonably close to it. Okay. So again, all we did is rewrote our equation in this form, and the computer is going to give us the slope. So when we do the experiment, we know what a is. Now, one thing that's very important is that a is the slope of the graph, so it has units as well. I'm going to make up some number. Let's say we did this experiment, and the computer is going to tell us that a is 12. It would have units of centimeters per gram. The computer will definitely not tell you what the units are, but you need to know them. And again, it's a slope. So remember, slope is like a change in the vertical scale, which is in centimeters, or a change in the horizontal scale, which is in grams. So what we do with the data, we take this table, we plot it and take the best fit line, and that gives us A. There might be reasons for other examples where we would want the intercept either instead of the slope or in addition to it. But we don't care what B is in this case. We might want to check to see it's close to 0. That'll give us some idea of how good our experiment was. And if B was significantly different than 0, maybe we'd have a, want to recheck our results. But our main goal is to get A. And so again, this is the slope according to the data. And so this should be equal to G over K. And our goal is to find K. So let's just solve this for K. So K would be, in this case, G divided by 12 centimeters per gram. And this is why I mentioned that you really want to pay attention to units here, because we want a numerical value for K along with the units. So G is 9.8 meters per second squared. And then we're dividing by K, which is 12 centimeters per gram. Okay. And here we've got meters and centimeters. We want to put a conversion factor in there as well. Say 100 centimeters and 1 meter, and then those will cancel out. And our units are grams per second squared. we could just leave it like that, but let's also convert it to kilograms. So we'd have, let's see, 1 kilogram is 1,000 grams. Now, when we actually talk about forces and Newton's laws and springs, these are correct units. Kilograms per second squared. Those are the right units for spring, but we usually write it in a different way. Like in something called, the basic units are newtons per meter, which is probably what we'd want to write it as, but that's equivalent to this. So anyways, numerically we'd have 9.8 over 120, and that would be kilograms per second squared. And so that's how we'd use, and we used all of our data to get this result. So, yeah, this is a very important topic overall. How to use your experimental data to get what you're looking for. And this is just one example, and it turns out this was kind of an easy example. And the reason it was easy is because the relation between our data, the mass and the stretch, those are, according to our theory, these are linear. So when we plot them, they fall on a line. But what if the data is not linear? And so, and a lot of times it won't be. And so that's a little bit more complicated, but we'll do an example of that as well. Okay, so here's how we would find, say, the spring constant in this case. And I want to do one example where we have non-linear data. I think I'll do that in a separate video. So I'll keep these short, and yeah, I'll record that in a separate video. So, and then I think I'll have a third video where we just talk a little bit about the assignment itself. So that'll be it for this one.